Hello everyone, I am Brewster Roy. I am currently pursuing my 4th year PhD in the Department of Physics, Indian Institute of Science, Bangalore. In this NPTEL GATE Physics course, I will be discussing some previous year's GATE Physics questions and try to solve them with proper explanations. This question is from the GATE Physics paper 2021. There is a numerical answer type 2 marks question and the topic of the question is electromagnetic theory. According to the question, consider a cross-section of an electromagnet having an air gap of 5 cm as shown in the figure. It consists of a magnetic material having magnetic permeability mu equals to 20,000 times mu naught, where mu naught is the magnetic permeability of vacuum and is driven by a coil having N times I equals to 10 to the power 4 amps, where N is the number of turns and I is the current in ampere. Now it has been said, ignoring the fringe fields, the magnitude of the magnetic field B vector in Tesla rounded off to 2 decimal places in the air gap between the magnetic poles is. So basically we have to find the magnetic field vector B in this air gap. Now let us see the solution part. According to the question, we have to deal with a magnetic circuit, which is basically analogous to an electrical circuit. First, we will study briefly about the concept of magnetic circuit. We know magnetic flux lines in a material form closed loop. If magnetic flux associated with a particular distribution of currents is confined to a well-defined path, then the system is known as magnetic circuit, which is analogous to an electrical circuit. Let us see an example now. We will consider a magnetic circuit which is basically an electromagnet consists of a core material having high magnetic permeability. The number of turns in the windings is capital N. The current through the wire is I. Now we will consider a closed path ABCDA, along which we will apply the Ampere's circuital law, that is dotted line in the figure. So we get a closed path integral of the magnetic field vector H is N times I. Now we will calculate the magnetic flux phi over the cross-section area S in the circuit. Now according to the Ampere's circuital law, the closed path integral of H vector is Ni. Now closed path integral is taken on the closed path ABCDA. Now we know our B vector is basically mu times H vector, where mu is the magnetic permeability of the core material. Now flux is defined as B times the cross section, that is B into S. We can write our H vector as B by mu. Now B is basically phi by S, so our H vector is phi by mu S. Now we will use the equation 2 in equation 1. Now equation 2 was our magnetic field vector H is equals to phi by mu S, and equation 1 was from the Ampere's circuital law, that is closed path integral of H vector is Ni. So if we use the equation 2 in equation 1, then we will get closed path integral of the magnetic flux phi over dl by mu S equals to Ni. Now we are dealing with a magnetic circuit, so we expect that our magnetic flux phi is essentially the same over any cross section S. So we can take out the phi term outside of the integration, so we can get phi equals to Ni divided by closed path integral of dl by mu S, which is basically our closed path integral of H vector divided by closed path integral of dl by mu S. Now according to the Ohm's law for our electrical circuit, we know Current passing through a circuit I equals to EMF by resistance, where EMF is electromotive force, which is defined as closed path integral of the electric field vector inside the conductor, and the resistance is closed path integral of dl by sigma s, where sigma is the conductivity of the material and s is the cross section area. Similarly, for magnetic circuit we have magnetic flux phi equals to closed path integral of H divided by closed path integral of dl by mu s. Now, by analogy with our electrical circuit, the quantity closed path integral of H vector is defined as magnetomotive force, which is MMF, and this closed path integral of dl by mu s, which is analogous to a resistance term in the electrical circuit. So, this closed path integral of dl by mu s is reluctance of the magnetic circuit. So, we have the working formula, that is magnetic flux phi equals to MMF, which is closed path integral of H vector divided by reluctance, that is closed path integral of dl by mu s. Now, we will see what happens if a small air gap is present in that magnetic circuit. To measure the magnetic field in a magnetic circuit, it is a common practice to have small air gap in that circuit. Let us consider this schematic now. In the schematic, there is an electromagnet and there is a small air gap in that magnetic circuit having length del L. Now, current passing through the electromagnet is I and number of turns is capital N. Core material is iron or any magnetic material with high magnetic permeability mu. So, according to our definition of reluctance, the reluctance of the core material Rc is basically Lc by mu s, where Lc is the core length, which is basically this closed path length A, B, C, D, E, F, A minus this air gap, that is del L. Mu is the magnetic permeability of the core and S is the cross section area in that core material, that is shown here. So, the reluctance of this air gap in that magnetic circuit is Ra equals to del L by mu naught S, where mu naught is the magnetic permeability in this air. Here, del L is very less than the core length Lc, so that spreading of magnetic flux in air gap is negligible and the effective cross section of the air gap can be taken same as that of the core material. So, total reluctance of that magnetic circuit is Rm equals to Rc plus Ra, where Rc is the reluctance of the core material and Ra is the reluctance of the air gap. So, it is analogous to the electric circuit where two resistors are connected in series. So, in our magnetic circuit, the total reluctance of that magnetic circuit is Lc by mu s plus del L by mu naught s. Now, we know the flux through the circuit phi is defined as MMF, that is magnetomotive force, divided by Rm, that is total reluctance of the magnetic circuit. So, in our present configuration, the magnetic flux in that magnetic circuit, that is phi, equals to N times I, which is basically MMF, magnetomotive force, divided by the reluctance of the circuit, that is Lc by mu s plus del L by mu naught s. From here, we can get the magnetic field in the air gap, that is V is equal to phi divided by the s cross section equals to Ni divided by Lc by mu plus del L by mu naught. So, this is our formula for magnetic field in that air gap. Now, according to the question, we have to consider this configuration of electromagnet with a air gap having length 5 cm. Now, according to the magnetic circuit, the N times I is 10 to the power 4 amps. The air gap in that magnetic circuit del L is 5 cm. Now, we will see what is the core length of this magnetic circuit, that is Lc. For this, we will consider this red dotted closed path inside the magnetic circuit. The closed path is passing through the center of each part of magnetic circuit. Now for this closed path, we'll first calculate the length of this side, the longer side. So as you can see, from here to here the length is 3 centimeters. So for this closed path, this length is half of that, that is 1.5 centimeter. And from here to here it is 3 centimeter. And from here to here it is the length of the air gap, that is 5 centimeter. And again from this to this part is 3 centimeter. And similarly the remaining part will be 1.5 centimeter. So if we sum up all of the lengths, then we'll get the length of this side is 14 centimeter. Now we'll see what is the length of this smaller side. So according to the schematic, from here to here the length is 1.5 centimeter, and this part will have length 3 centimeter, and similarly the remaining part will have 1.5 centimeter. So if we sum up all of this length, then we will get the length of this smaller side is 6 centimeter. So our core length will be the length of this closed path minus this air gap. So this is basically 14 times 2 plus 6 times 2, and we will subtract the air gap, that is 5 centimeters. So we will get the core length as 35 centimeter. The magnetic permeability of the core material is 2 into 10 to the power 4 times mu naught, where mu naught is the magnetic permeability of air, that is 4 pi times 10 to the power minus 7 Henry per meter. So in the previous slide, we came to know about all the quantities required to calculate the magnetic field in the air gap. So magnitude of the magnetic field in air gap is B equals to Ni by Lc by mu plus del L by mu naught. So if we put the value of each quantity, then we'll get Ni equals to 10 to the power 4, and Lc is 35 times 10 to the power minus 2 meter divided by 2 into 10 to the power 4 mu naught, plus del L is 5 into 10 to the power minus 2 meter and mu naught divided by mu naught. So if we see this expression carefully, the first term in the denominator can be neglected, as this mu is 2 into 10 to the power 4 mu naught, which is very greater than mu naught. So if we cancel out this term, we will get the simplified magnetic field, that is 10 to the power 4 divided by 5 into 10 to the power minus 2 by 4 pi into 10 to the power minus 7. So if we calculate that, we will get 4 pi divided by 5 into 10 to the power minus 1 Tesla. So our magnetic field in the air gap will be 0.25 Tesla, which is rounded off to first two decimal terms. So we have solved the problem, and we found that the magnetic field in this air gap is around 0.25 Tesla. This question is from the GATE Physics paper 2021. This is a numerical answer type 2 marks question, and the topic of the question is electromagnetic theory. So the question is, consider two concentric conducting spherical shells as shown in the figure. The inner shell has a radius small a and carries a charge plus q. The outer shell has a radius small b and carries a charge minus q. The empty space between them is half filled by a hemispherical shell of a dielectric having permittivity epsilon 1. The remaining space between the shells is filled with air having the permittivity epsilon naught. The electric field at a radial distance small r from the center and between the shells, that is r greater than a but less than b, is, four options are given. Option A is q by 2 pi times epsilon naught plus epsilon 1 times r squared along the r cap direction everywhere. Option B, q by 4 pi epsilon naught multiplied with 1 by r square along the r cup direction on the air side, and q by 4 pi epsilon 1 multiplied with 1 by r square along the r cup direction on the dielectric side. Option C, q by 2 pi epsilon naught multiplied with 1 by r square along the r cap direction on the air side, and q by 2 pi epsilon 1 multiplied with 1 by r square along the r cap direction on the dielectric side. Option D is q by 4 pi times epsilon naught plus epsilon 1 multiplied with 1 by r square along the r cap direction everywhere. So let us see the solution part. According to the question, we are given two concentric spherical shell. The inner shell has the radius small a and the outer shell has the radius small b. As the spherical shells are conducting, the plus q charge will be uniformly distributed over the surface of the inner shell, and the minus q charge will be uniformly distributed over the outer shell. The empty space between the two shells is half filled by the hemispherical shell of a dielectric having permittivity epsilon 1, and the remaining part is air having permittivity epsilon naught. Now the dielectric in the region between these two spherical shell, that is hemispherical part, will be polarized, and because of the polarization there will be formation of bound charges in this dielectric medium. Now the displacement vector in the air is given by d naught vector equals to epsilon naught times electric field vector E, and in dielectric it will be d1 vector equals to epsilon 1 times E vector. We only have the information about the free charges, not the bound charges according to the question. So we will use the Gauss law in terms of the d vector, that is surface integral of the d vector is free charge enclosed by this surface. So according to our schematic, the closed surface is the dotted line. So the free charge enclosed by the surface is only plus q. So we can write this surface integral as d naught times 4 pi r square by 2, which is the surface area of the closed surface in the air region, that is 4 pi r square by 2, plus d1 times 4 pi r square by 2, which is also the surface area, that is the half of the spherical surface area in the dielectric region, and the free charge enclosed by the surface is plus q. So we can take this 4 pi r square by 2, that is 2 pi r square, as common, and we will have 2 pi r square times d naught plus d1 equals to q. We can write it as 2 pi r square times epsilon naught e plus epsilon 1 e. So which is basically our displacement vector d naught and d1 equals to the free charge enclosed by the closed surface, that is plus q. So we'll take E, the electric field, as common. So we'll get 2 pi r square E times epsilon naught plus epsilon 1 equals to q. So our electric field is q by 2 pi epsilon naught plus epsilon 1 times 1 by r square. The direction of the electric field in the region r greater than a but less than b region will be along radial direction, that is r cap direction, as the charge distribution on the spherical shell surface is spherically symmetric. So the electric field vector in the region will be q by 2 pi times epsilon naught plus epsilon 1 times 1 by r square along the r cap direction. So our option A is correct. So according to our solution, the electric field at a radial distance small r from the center and between the shells, that means in this region, is option A, q by 2 pi times epsilon naught plus epsilon 1 multiplied with 1 by r square along the r cap direction, that is radial direction, everywhere. This question is from the GATE Physics paper 2021. This is a MSQ having 1 mark and the topic of the question is electromagnetic theory. The question is, as shown in the figure, an electromagnetic wave with intensity I with subscript I is incident at the interface of two media having refractive indices n1 equals to 1 and n2 equals to √3. The wave is reflected with intensity I with subscript R and transmitted with intensity I with subscript capital T. Permeability of each medium is the same. The reflection coefficient is defined as capital R equals to I with subscript R divided by I with subscript I, and the transmission coefficient capital T is defined as I with subscript T divided by I with subscript I. So we have to choose the correct statement. Option A is R equals to 0 if theta I equals to 0 degree and polarization of incident light is parallel to the plane of the incidence. Option B, T equals to 1 if theta I equals to 60 degree and polarization of the incident light is parallel to the plane of incidence. Option C, R equals to 0 if theta I equals to 60 degree and polarization of the incident light is perpendicular to the plane of incidence. And option D, T equals to 1 if theta I equals to 60 degree and polarization of the incident light is perpendicular to the plane of incidence. So as this is a MSQ, so it is possible to have multiple options correct for this question. Let us see the solution part now. According to our question, we have an interface separating two media having refractive indices n1 equals to 1 and n2 equals to √3. Now, one unpolarized light is incident on the interface with angle of incidence theta I and the angle of reflection is theta R and the angle of transmittance is theta T. Now, the reflection coefficient R is defined as IR by II and the transmission coefficient is defined as T equals to IT by II, where IR is the intensity of the reflected light and II is the intensity of the incident light and IT is the intensity of the transmitted light. Now we will first calculate the Brewster angle theta B at the interface. First let us discuss what is the Brewster angle theta B. So Brewster angle theta B is basically the angle of incidence of an unpolarized light on an interface such that the reflected light will have only the component of S polarized light. That is, the reflected light will have electric field only the perpendicular direction of the plane of incidence. There will be no component with the electric field in the parallel to the plane of the incidence. That is, p polarized light will not be there. So according to the Fresnel's equation, the reflection coefficient for the p polarized, that is the parallel component, is tan of theta I minus theta t divided by tan of theta I plus theta t, and the reflection coefficient for the S polarized light, that is the perpendicular electric field to the plane of incidence, is minus sine theta I minus theta t divided by sine of theta I plus theta t. Now if we look into these relations carefully, we can see for the first relation, if the theta I plus theta t is 90 degree, then this tan of theta I plus theta t is infinity. So effectively we will get this R parallel is 0. But for this condition theta I plus theta t equals to 90 degree, this R perpendicular is not equal to 0. So from this condition we can get the estimation of Brewster angle. So under the condition of theta I plus theta t equals to 90 degree, only the S polarized light, that is the light with electric field in the perpendicular direction of the plane of incidence, will get reflected and theta I will be known as Brewster angle. Now we will use the Snell's law to estimate the Brewster angle. Now under this condition, the angle of incidence theta is basically our Brewster angle, that is theta b. So by applying this Snell's law, we will get sine theta b by sine theta t equals to n2 by n1. Now our theta t is basically 90 degree minus theta b according to our condition for Brewster angle. So effectively we will get sine theta b by cos theta b. So our n2 by n1 basically sine theta by cos theta b, that is tan theta b equals to n2 by n1. Now according to our question, n2 value is √3 and n1 equals to 1. So in our case the Brewster angle is tan inverse n2 by n1, that is tan inverse √3 by 1. So theta b equals to 60 degree. Now we'll consider 2 points. First point is, if the polarization of the light, that is E vector, is in the plane of incidence, that is P polarized light, then at the angle of incidence theta equals to theta b, we have the reflection coefficient equals to 0 and the transmission coefficient t equals to 1. So this is the case of total transmission of P polarized light at incidence angle theta b. And the second point is, if the polarization of light, that is E vector, is in perpendicular to the plane of incidence, so this is S polarized light, then at the angle of incidence theta equals to theta b, we have the reflection coefficient not equal to 0 as well as the transmission coefficient not equals to 1. So this is the case of partially reflected and transmitted light for the S polarization case. Also, for the angle of incidence theta equals to 0, that is normal incidence, the reflection coefficient not equal to 0. So if we consider all the points, then we can conclude only our option B is correct for this question. According to our solution, the correct option for this MSQ is only option B, that is T equals to 1, that is transmission coefficient equals to 1 if angle of incidence theta I equals to 60 degree and polarization of the incident light is parallel to the plane of incidence.